Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another topic. Let me write the topic. Some basic definitions. Let me underline it. Some basic definitions related to what? Actually, we want to discuss those definitions which serve as a kind of crystallographic language, right? And these definitions are such that they apply to 1, 2, or 3-dimensional crystals. So let us begin with the first definition, the crystal lattice. We have already discussed it. I'm refreshing it. Now in crystallography means when we are talking about crystals, discussing their properties. Now in that crystallography, only the geometrical properties of the crystal are of interest, rather than those arising from the particular atoms constituting the crystal, right? I repeat, in crystallography, only the geometrical properties of the crystal are of interest, rather than those arising from the particular atoms constituting the crystal. Therefore, what we do, we replace each atom by a geometrical point located at the equilibrium position of that atom. The result is a pattern of points having the same geometrical properties as the crystal, but which is devoid of any physical contents. Let me write it. The result is a pattern of points having the same geometrical properties as the crystal, but which is devoid of any physical contents, right? Now this geometrical pattern we call crystal lattice. Or simply the lattice. And all the atomic sites have been replaced by lattice sites. Now there are two classes of lattices. Two classes of lattices. Which two? One is called the Bravais. It is pronounced as Bravais Lattice. And the second one is called the non-Bravais lattice, right? Now, what is the difference? You need to remember, in the Bravais lattice, all lattice points are equivalent, and hence by necessity, all atoms in the crystal are of the same kind. If we write it, in a Bravais lattice, all lattice points are equivalent, and hence by necessity all atoms in the crystal are of the same kind. We have to remember, when we talk of Bravais lattice, all points, lattice points are equivalent. I underline this word equivalent, and that means all atoms in the crystal are of the same kind, right? On the other hand, in a non-Bravais lattice, some of the lattice points, are non-equivalent. Remember it. Let me draw a figure. Then we will move forward. So this is a figure. Let me name it figure 1. Let me show some points in it with this color. Let me name some sites with this color. This is A, this is B, this one C, and this point here, A prime, this prime point B prime, and this point C prime. What is it? It is a non-Bravais Bravais Lattice. Look at it, think about it. Yes. Now in this figure 1, it is clear that the lattice sides A, B, C are equivalent. The lattice sides A, B, C are equivalent to each other, and so are the sides A prime, B prime, C prime, right? Among themselves. Among themselves. This is important. A, B, C are equivalent to each other among themselves. A prime, B prime, C prime are equivalent also among themselves. But the two sides, A and A prime, are not equivalent. Are not equivalent to each other, as can be seen by the fact that the lattice is not invariant under a translation by AA dash. Try to understand it. I'm saying AA dash are not equivalent to each other because the lattice is not invariant under the translation by AA dash. If you translate a whole lattice this way by a vector joining A and A dash, this will not appear the same. So it is not invariant under that translation. That's why AA prime are not equivalent, right? This is so whether the atoms A and A prime are of the same kind, for example, two hydrogen atoms, or of different kinds, for example, hydrogen and chlorine atom, right? Another important thing is the non-Bravais lattice, the non-Bravais lattice may be regarded as a combination of two or more interpenetrating Bravais lattices with fixed orientations relative to each other, relative to each other. Thus, in this figure 1, which is a non-Bravais lattice, the points in A, B, C form one Bravais lattice and other points similar to them, while the points A prime, B prime, C prime, etc. form another Bravais lattice. right? Overall, it is a non-Bravais lattice, but we can consider it as combination of two Bravais lattices with fixed orientations relative to each other. So A, B, C and all similar points like them form one Bravais lattice, while points A prime, B prime, C prime and all similar points form another Bravais lattice, right? So let us move to the next definition. Basis vectors. Now consider the lattice shown in figure 2. Let me draw first figure. Let me draw it differently. So let me name some points. It means the same color here. Let me name some points. Let this point be A, this B, this C, this one D. So I have labeled 4 points A, B, C, and D. And let me select some point here. And let this point be the origin. A is origin. This is origin. Now I name another point here as F. Now I locate a point with vector R relative to origin. Let this be R. Let me use now another color. Let this be little a vector and this be little b vector, and I name some other points. I'll locate some other points. This point, this point, this point. Here I have a point. So this is my figure 2. We have to define basis vectors now. Now consider this lattice shown in figure 2. Now let us choose the origin of coordinates at a certain lattice point, say A. So at A, we choose the origin of coordinates, right? Now the position vector of any lattice point can be written as Rn equal to N1A plus N2B, where A, B are two vectors shown. You can see we have selected two little vectors A and B. I am saying if Rn represents the position vector of any lattice point in general, it can be written as N1A plus n2b, where n1, n2 is a pair of integers. n1, n2 is a pair of integers. So in this lattice, you can write position vector of any lattice point using this equation in terms of these little vectors a and b, where n1, n2 is a pair of integers, and in the figure we have located one of the lattice point using R. Rn stands for general position vector of any lattice. So one R we have shown in the figure. So you can see n1, n2 is a pair of integers whose values depend on the lattice point. For the point D, this point, what is n1, n2? It is 0 and 2. For D, n1, n2 is 0 and 2. Right? Because along this axis is 0 units away, but along this axis it is 2 units away, 1 unit and second unit. So it's n1, n2 is 0 and 2. For B, n1 and 2 is what? 1 and 0. Because along this axis it is not away. So for B, it is n1, n2 is 1 and 0. What about F point? For F point, n1, n2 is 0 and minus 1, because we are taking upward direction as positive. It is located downward to the origin. So for F, n1, n2 is 0 and minus 1. 0 and minus 1. Right? Now the two vectors A and B, which must be non-collinear, the two vectors A and B, which must be non-collinear, form a set of basis vectors for the lattice, right? So A and B here forms a set of basis vectors for this lattice. What is the property of these basis vectors? Property is, in terms of these, we can express the positions of all lattice points using equation 1. Let me name it equation 1. So using equation 1, in terms of basis vectors A and B, we can express the position of all the lattice points, right? Now the set of all vectors expressed by equation 1 is called the lattice vectors. Now Rn's are lattice vectors. A and B are basis vectors, right? We may also say that the lattice is invariant under the group of all the translations expressed by equation 1. This is often rephrased by saying that the lattice has a translational symmetry under all displacements specified by lattice vectors Rn. This fact we have already discussed, that lattice has a translational symmetry, right? Let's move forward. Now, the choice of basis vectors is not unique. This is important. The choice of basis vectors is not unique. Thus, one could equally well take the vectors that we show in the figure first. This is my A. Let me use another color. I think red. With this, I define another vector here. And I name it B prime. Let me clear it first. This is B prime. If you see, this B prime is the resultant of A and B. If this is A, this is B. Now parallelogram is completed. So B prime is A plus B. Here B prime is A plus B, as seen in the figure, as is clear in the figure. A plus B is B prime. Now, if you see in this figure, we could equally well take vectors A and B prime as a basis, right? We could equally well take the vectors A and B prime as a basis. That means you can also express position of all the lattice sites in terms of these vectors A and B prime. And other possibilities are also evident. The choice is usually dictated by convenience, right? We need to remember it that the choice of basis vectors is not unique. There are multiple possibilities. So let's move to next definition. The unit cell. What is unit cell? Now the area, let me write it. We are talking in 2 dimensions, therefore we are talking of area. In 3 dimensions, instead of area, we will have volume. Now the area of the parallelogram whose sides are the basis vectors A and B is called a unit cell of the lattice. I repeat, the area of the parallelogram whose sides are the basis vectors A and B is called a unit cell. In that, if such a cell is translated by all the lattice vectors represented by equation 1, the area of the whole lattice is covered once and only once. Now, the unit cell is usually the smallest area which produces this coverage, right? Therefore, the lattice may be viewed as composed of a large number of equivalent unit cells placed side by side. Now the choice of a unit cell for one and the same lattice is not unique. Let me show in the figure. Let me shade this. This is if you take A and B as your basis vector, this is A, this is B, right? This is A, this is B, then this is the area, then this is unit cell, right? But if I take A and B prime as basis vectors, then unit cell is different. I will use different color. This is my A, this is my B dash. Let me draw it and shade it. This is also unit cell. The difference, if I take basis vectors A and B, then this is unit cell in black. If I take A and B prime as basis vectors, A and B prime as basis vectors, then this is the unit cell which is in blue, right? Let us move. So you got the idea that the choice of a unit cell for one and the same lattice is not unique for the same reason that the choice of basis vectors is not unique, right? And as we said, the choice is dictated by convenience. Now, some remarks which you need to remember. Remarks. First, all unit cells have the same area. All unit cells have the same area. Thus, the cell formed by A and B has this area modulus of A cross B, while that the cell formed by A and B prime has the area S prime modulus of A cross B prime. But S prime is same as S. You can see how I can write S prime equal to A plus B. Why? Because as I said, B prime is A plus B. Here, B prime is A plus B. So I write S prime as A cross B prime. I replace B prime by A plus B. Now it will be just A cross A plus A cross B. That is just A cross B, which says why? Because A cross A is 0. So when you distribute this cross product over this addition, it will be A cross A plus A cross B. The first term will be 0 because if you cross a vector with itself, you get 0. You can see area of unit cell with basis vectors A and B is same as area of unit cell with basis vectors A and B prime, right? Therefore, the area of each unit cell is unique, even though the particular shape is not. shape of the unit cell is not unique. This has one shape, this is another shape, because basis vectors are different, but their areas are equal, right? Now, second thing which you need to remember is how many lattice points belong to a unit cell. How many lattice points belong to a unit cell? If you ask this question, how many lattice points belong to a unit cell? If you look at this figure, this is your one cell, it appears that 4 points belong to a unit cell. We are talking in 2 dimensions here. Now, if you check the unit cell formed by A cross B has 4 points at its corners, or same is true with the unit cell formed by A and B prime basis vectors. But you need to think about this thing, that each of these points is shared by 4 adjacent cells. I repeat, the unit cell has 4 points at its corners, but each of these points is shared by 4 adjacent cells. This point is shared by this cell, this cell, this cell, and this cell. Same is true for all points. Hence, each unit cell has only one lattice point. Each unit cell has only one lattice point. Each unit cell has only one lattice point. I hope you got it. Now, the unit cell we discussed is called a primitive cell. Primitive cell. This kind of unit cell which we discuss is called a primitive cell. It is sometimes more convenient, we will discuss that, to deal with a unit cell which is larger than the primitive cell. That kind of cell is called non-primitive. We will discuss that in next lecture. So I will stop here. I will summarize. So we said that how we define crystal lattice. Then we said there are 2 classes of lattices, Bravais and non-Bravais. Then we said, showed a non-Bravais lattice and said that a non-Bravais lattice can be considered as a combination of 2 or more interpenetrating Bravais lattices with fixed orientation relative to each other. Then we talked about basis vectors in B, and we said that the choice of basis vectors is not unique, and you can have multiple possibilities, as we said and discussed. And then we talked of the unit cell in 2 dimensions. There is the area of the parallelogram whose sides are the basis vectors. We said the choice of unit cell is not unique, but what is unique? The area of a unit cell, as we showed, S is equal to S prime. And this kind of unit cell which we discuss is called a primitive unit cell. So this is all for today. Don't waste your time. Go through all the video lectures and don't forget to like, share, and subscribe my channel. You can also give comments in the comment box. Thank you. God bless you. Assalamu alaikum.